Hi students, so welcome back. So today's unit is about units and scales. We know that the chemists, right, we use a lot of analytical instruments here and we need some kind of units to quantify the kinds of data we are using here. So analytical results must always have value, a numerical value for validations, calibrations, and range, right? And also for uncertainty annotations there. So there must be a unit associated to most of these data that we calibrated from an instrument here, right, for traceability. So the next time when we want to do some referencing in other locations or comparison with other kinds of research data, we have something to compare about. So the measurement of a traceability is a property of a measurement result, whereby the result can be related to a reference through a document unbroken chain of calibrations here. So that means it doesn't matter where you are in the world here. If you're using a kilogram here, the same kilogram definition persists through everywhere. It is universal, right? So each of these calibration contribute a measurement of uncertainty based on the instrument itself. Now, in units and scales, in this topic here, we will be discussing two portions here, right? The trouble with parts per scale as well as a unit conversion here, right? So the trouble with parts per, notice parts per pp scale, right? I'll talk a bit more, but if you know about the IUPAC BIPM, right? IUPAC stands for the International Unit of Pure and Applied Chemistry here. Right, why BIPM? BIPM is actually in French. It's headquarters in France, more in Paris. So BIPM stands for the Bureau International des Poids et Mesures. Right. So in translation, in English, it just stands for the International Bureau of Weights and Measures. And ISO, International Organization for Standardizations, right? They discourage the use of parts per notation. When I say parts per, means ppm, ppb, you know, parts per million, parts per billion. Why is that so, right? Because, right, these notations may not be unequivocal because of language barrier. So PPT, to people normally, they don't do science, oh, PowerPoint, right? But PPT in science, it could be parts per thousands, right? Or parts per trillion. And that differs by a lot, right? Using the word PPT. So billion is 10 power 9, right? In English speaking countries, but 10 power 12 in some other language. The billion in French is like 10 power 12, not billion, 10 power 9. So it's 1,000 space difference, right? So there's also the issue whether it is a mass fraction or mole fraction here, because when using parts, right, so it's like a fraction, like a proportion, there's no unit for that. So we are unsure whether it is like a mass per mass or mole per mole, right? So there can also be confusion in another way, like for instance, right, 350 ppm, right, parts per million of CO2 in the air is 350 molecules of CO2 per 1 million molecules of atoms in the air, right? Not 350 micrograms of CO2 per gram of air. So by using 350 ppm of CO2 here, this chemist that you know is about the molecules, right? In terms of the molecules, it's not about the mass, right? But these are things that you could do, go deeper and learn deeper to know it. If not, there'll be confusion, and that's exactly why we try to stay away from using pp, parts per kind of annotations here. Now the next part is about the unit conversion here. So there are some things you got to know here. This is the list, right, you see on the slide here that you should know. Number one is this Avogadro's law. You learn in secondary school or in the past in somewhere else. Avogadro's law talks about two given samples of ideal gas, IG, of the same volume, temperature, and pressure. They contain the same number of atoms and molecules, right? So to me, this law is summarized as number of moles is equals to number of substance. The substance could be molecules, atoms, ions, particles. The space is just filled, right, over the Avogadro's constant, 6.0223 times 10 power 23. The next law you got to know is the ideal gas law, the IG law, which is summarized as PV equals nRT. You learn in your physical chemistry courses, but let's just do a quick recap here. If we have PV nRT, so the pressure is in Pascal, the volume is in liter, and the number of moles, R, is a gas constant 8.314 here. temperature is in Kelvin, and we assume that it is a perfectly elastic collision, and there's no interaction or kinds of intermolecular forces between the particles, atoms, and molecules here. We assume it's completely elastic. That means they do not react together and stick together here. They bounce off with conservation of energy. And the other part is that the size of the particles is negligible compared to the size of the container, right? And we also assume that all particles are in continuous fluid motion here. Okay. Next part is the R, the gas constant 8.314, right? That's in joules per mole per Kelvin. It is a product of the Avogadro's constant and the Boltzmann's constant. Then we have the molar volume of the ideal gas, which is 2.24 liters at STP, standard temperature and pressure, right? Which is 0 degrees Celsius and 1 atmosphere. Okay. And this molar volume of an ideal gas is equivalent to 24 liters or dm cube at room temperature RTP, which we do not as just room temperature and pressure. So the last part is about the gas concentration. So the ppm scale, right, converting to the partial pressure is easy using the Dalton's law of partial pressure. Like for instance, you have got 5 parts per million, right, is the atmospheric partial pressure of pollutants per 1 atmospheric pressure of the total air pressure. So once again, so 5 ppm, 5 parts per million is 5 atmospheric partial pressure of pollutants per 1 atmospheric pressure of the total air pressure. And with that, we sum up our portions of the units and scales, and this also brings us to the end of this topic here. I would thank you very much for watching this, and I hope you enjoy our presentation. Cheers.